Measurements are everywhere. They are an integral part of our daily lives, often going unnoticed but always essential. We use them every day in countless ways, from the moment we wake up to the time we go to bed. Want to bake a cake? You'll need to measure the flour, sugar, and milk. Precise measurements ensure your cake turns out just right. Building a house? Better measure those walls and beams. Accurate measurements are crucial for a sturdy and safe structure. Measurements are the foundation of science and engineering. They allow us to quantify and understand the physical world. Scientists use measurements to understand how the world works. They record data meticulously to make groundbreaking discoveries. Engineers use measurements to design and build amazing things, from bridges to spacecraft. Precision is key in their work. Without measurements, we'd be lost. Our world would be chaotic and unpredictable. We wouldn't know how tall we are, how much something weighs, or how far away a star is. Measurements give us clarity. Astronomers measure distances to stars and galaxies, helping us understand the vastness of the universe. Measurements help us make sense of the world around us. They bring order and understanding to our lives. So the next time you measure something, remember, you're not just using a ruler or a scale, you're tapping into the language of the universe. Every measurement connects you to a grand tradition of discovery and precision. Imagine trying to build a house without agreeing on what a meter is. Chaos. That's why we need standard units. A unit is a fixed quantity of something, like a meter for length, a kilogram for mass, or a second for time. These units give meaning to our measurements. We use an internationally agreed-upon system called the International System of Units, SI. It's like a universal language for measurement. The SI system makes it easy for scientists and engineers all over the world to share their work. It's like speaking the same language, the language of measurement. Scientists and engineers have a whole toolbox of instruments to measure the world around us. We can classify these instruments in different ways. One way is to look at whether they measure a quantity directly, also known as absolute instruments, or by comparing it to a known value, which we call secondary instruments. For example, a ruler directly measures length, while a spring scale compares weight to the extension of a spring. We can also classify instruments based on whether they need an external power source. Active instruments like digital multimeters do. Passive instruments like mercury thermometers don't. Understanding these classifications helps us choose the right tool for the job. When it comes to measuring, accuracy is key. That's where null-type and deflection-type instruments come in. Null-type instruments are like balancing scales. They compare the measured quantity with a known value until they reach a null point. A potentiometer used to measure voltage is a good example. Deflection-type instruments, on the other hand, show the measured value by how much a pointer moves on a scale. Think of a pressure gauge or a car speedometer. Both types have their pros and cons. Null-type instruments are generally more accurate, while deflection-type instruments are often faster and easier to use. Section 5. Smart instruments, the future of measurement. Hold on to your hats, because measurement technology is taking a giant leap forward with smart instruments. These high-tech wonders combine sensors, processing power, and communication capabilities to provide more accurate, reliable, and convenient measurements than ever before. Smart instruments can automatically calibrate themselves, detect and correct errors, and even communicate with other devices. Imagine a world where your thermostat talks to your oven to optimize energy consumption. From smartwatches that track our fitness to self-driving cars that navigate our roads, smart instruments are transforming the way we live, work, and interact with the world. Section 6. Performance matters. Understanding instrument characteristics. Not all measuring instruments are created equal. Some are faster, some are more accurate, and some are better suited for certain tasks. That's why it's important to understand their performance characteristics. Static characteristics describe how an instrument behaves when the measured quantity is constant. These include accuracy, precision, resolution, and sensitivity. Dynamic characteristics, on the other hand, come into play when the measured quantity is changing. These include response time, settling time, and bandwidth. By understanding these characteristics, we can choose the right instrument for the job and ensure accurate and reliable measurements. Section 7. Errors. The uninvited guests in measurement. Even the most sophisticated instruments can't escape the clutches of errors. These errors can be subtle or glaring, but they are always present. Errors are deviations from the true value of a measurement. They can distort our results and lead to incorrect conclusions if not properly accounted for. They can creep in from various sources like limitations in the instrument, environmental factors, or even human mistakes. For instance, a slight change in temperature or humidity can affect the readings. We can classify errors into different types: systematic errors, random errors, and gross errors. Each type has its own characteristics and sources. Systematic errors are consistent deviations caused by factors like instrument calibration or environmental conditions. These errors can often be predicted and corrected. Random errors are unpredictable fluctuations that occur randomly. They are often due to unknown or unpredictable factors and can be more challenging to manage. And gross errors are large, often human-induced errors. These can be due to mistakes in reading instruments, recording data, or even simple calculation errors. While we can't eliminate errors entirely, we can certainly minimize them by calibrating our instruments, controlling environmental factors, and using proper measurement techniques. Regular maintenance and training can also help in reducing the impact of these uninvited guests in our measurements. Section 8. Analog instruments, the classics. Analog instruments, the old-timers of the measurement world, are still alive and kicking. These instruments display measurements using a continuous scale, like a needle moving on a dial. One classic example is the Permanent Magnet Moving Coil, PMMC instrument. Used in ammeters and voltmeters, it relies on the interaction between a magnetic field and a current-carrying coil to deflect a pointer. Other examples include pressure gauges, thermometers, and even the humble clock on your wall. While digital instruments gain popularity, analog instruments remain valuable for their simplicity, affordability, and immunity to electromagnetic interference. Section 9. Electronic enhancement, analog instruments, get an upgrade. Analog instruments may be classic, but they're not stuck in the past. With the help of electronics, they've gotten a modern makeover. Electronic instruments combine the simplicity of analog displays with the power of electronic circuits. One example is the rectifier, which converts AC voltage to DC voltage for measurement by a PMMC instrument. Another is the cathode ray oscilloscope, CRO, which uses an electron beam to display waveforms on a screen, allowing us to visualize and analyze electrical signals. These electronic enhancements have expanded the capabilities of analog instruments, making them even more versatile and powerful tools for measurement. Section 10. Digital dominance, the rise of digital instruments. Hold on tight, because the digital revolution has taken the measurement world by storm. The transformation from analog to digital has been swift and impactful. Digital instruments are everywhere, from our smartphones and watches to sophisticated laboratory equipment. These devices have become integral to our daily lives and scientific endeavors. Digital instruments convert measured quantities into digital signals, which are then displayed using numerical displays or graphs. This conversion process ensures that the data is precise and easy to interpret. This digital representation offers numerous advantages over analog counterparts, including higher accuracy, better resolution, and the ability to store and process data efficiently. The ease of data manipulation and storage is a game changer. Examples of digital instruments abound, from the ubiquitous digital multimeter, capable of measuring various electrical quantities with remarkable precision, to the powerful digital oscilloscope, used to analyze complex waveforms with incredible precision. These tools are indispensable in both educational and professional settings. Digital instruments are revolutionizing the way we measure and understand the world. They provide us with the ability to capture, analyze, and interpret data like never before, paving the way for new discoveries and innovations. Section 11. Measurement Mastery, a universe of applications. Congratulations! You've journeyed through the fascinating world of measurement. From the fundamental concepts to the latest technological advancements, you've gained a solid understanding of this essential field. Remember, measurement isn't just about numbers and instruments. It's about understanding the world around us. From the vastness of space to the intricacies of the human body, measurement allows us to explore, analyze, and innovate. So embrace the power of measurement. Use it to satisfy your curiosity, solve problems, and create something amazing. The possibilities are as limitless as the universe itself.